All right. Good almost afternoon to everybody. Thanks for coming. This talk is JavaFX graphics tips and tricks. I'm Richard Bear, the Java client architect. Wow, that comes out yellow on the screen. So this talk is going to talk a lot about performance tips. And as with any talk on performance tips, you know, take a big healthy dose of caution on what you're going to see. You could go completely crazy and pre-optimize everything, and you'll be very sad if you do. So first, write clean code, then profile. If you find out you have problems, that's great. A lot of the things I'm going to talk about today are principles that are always true. It'll always be faster to say, write some little code loops in assembly than it is in some high level, say, JavaScript. Yeah, that's true. Well, is that going to make a big difference in your application? Most of the time, probably not. But in those few cases where it's important, it'll apply. Same sort of stuff for what we're going to talk about today. This is the state of the art in 2.2. In JavaFX 8, we've made a lot of improvements in performance, and so some things may not be that applicable in 8 that are presently applicable in 2.2. So for today, we've got our blackboard out, and here's our syllabus, what we're going to cover. We're going to talk about some performance numbers. I did some benchmarking yesterday, and I had some numbers that I wanted to show you, sort of give some context for where we're at. The second one is just overall rules or principles for good performance in JavaFX, and then a bunch of tips and tricks along the way to make stuff faster. So the first benchmark that I had results for was GUIMark 2 vector. So this test has been around since, I believe, 2007. And in this test, it basically draws a 4-level stock chart that's continuously animated. And I grabbed performance numbers for Chrome, Safari, Firefox, and IE9, all the latest versions, on Windows, Linux, and Mac OS to the degree that it was applicable. And then I had 2 different tests for JavaFX, one that uses the scene graph and one that uses the canvas node. So in the vector test on Windows, JavaFX was beating all 3 of the browsers. I did not test Safari on Windows. On Linux, I spent an hour and a half trying to get Chrome to install and failed. So I only have the number for Firefox there, in which case both the scene graph and canvas version of JavaFX did very well. And on the Mac, Safari beat us. But we got the other guys. Now, the interesting thing on this one is that you'll notice that on Windows and Linux, actually using the scene graph was faster than using canvas. So when we're going through the talk, just bear in mind that sometimes it's faster to use one technique, sometimes it's another. The only way you can really tell is to do it and profile it. So the next test that I did was GUIMark 2 Bitmap. This one has a tower and a bunch of little monsters, and the monsters run around and then the tower shoots them. And in this test, JavaFX is a lot faster than the browsers. I think part of it could be the difference between the execution speed of a JavaScript engine versus the execution speed of Hotspot. But these are just, I just ran these tests yesterday. Also interesting is that Canvas is way, way faster than all the other options. The JavaFX Canvas, that is, in this case. And on the browsers, it's all implemented using Canvas. Now, the next one we had was text, and here JavaFX did a pretty good job too. In the first one, you just sort of have to ignore the results on Windows because I was hitting 60 frames per second on the Windows machine for the browsers as well as FX, and we're all sort of rate limited at 60 frames per second so we don't use too much of your battery life. So there's not a whole lot of data that we can really acquire from looking at the Windows results. But the Linux and Mac OS X results are, again, pretty favorable for FX. Now, you can't really do text with Canvas, and so there's no JavaFX Canvas version. So it's just the scene graph version. So these were, these tests were not meant to be like official benchmark information. It's just, I just ran the things yesterday to see what would happen, and this is what happened. One of the things that we will be doing is taking our benchmark information and making it public so that everybody can run the benchmarks and find out for themselves on their own configurations where we're at. GUIMark 2 is a public benchmark. We just need to put out the JavaFX versions and then you guys can just run it. Now, I did another interesting comparison because, like I said, we've been doing a lot of performance work on JavaFX 8, and so I wanted to compare how 2.2 versus 8 went. And this is basically what we've done in JavaFX 8 is we've just about doubled our performance in each of these tests. And the last one's an approximation. But we've done a lot of work on making sure that JavaFX 8 was really fast. And a big part of it was all the work that we were doing for the kiosk and embedded and all the different demos has to be really fast on those low-end devices. And as a result, we got huge performance increases even on the desktop. So as we go through the rest of the session content, bear in mind that we're actually really fast to begin with. And so, but you can stress the system, and there are things that you can do that will help or hurt. So we'll go through this. The first rule to keep in mind whenever you're doing JavaFX is that if you want to make it faster, well, then do less work. One of the things you could do is you could just have fewer nodes in the scene graph. So here's a little mini scene graph here. And one of the things that we have to do is we have to apply CSS to the scene graph. So we're going to visit the first node, then the next, and the one after, then the next guy, and then another one. And then we're going to go and do layout. We're going to visit the first node, and then the next, another one, and another one, and another one. And then we're going to go do some mouse picking to make sure that we've got the hover state of the nodes correct. And that's going to require that we traverse the scene graph. Sometimes it goes through the whole scene graph. Sometimes it doesn't have to. There we go. And then we're going to have a rendering pass, which is going to do the same thing. It's going to have to visit everybody. We're going to have a dirty region pass where we compute which area of the scene graph is dirty and needs to be repainted. And that's going to have to visit everything. So there's a lot of iterative work that we have to do in terms of traversing the scene graph. So obviously, if you have an order of magnitude fewer nodes, there's going to be a lot less work that you have to do. So here's another little piece of advice, right? On your desktop system, man, you can get away with murder. But on smaller systems, such as the Panda boards, Beagle boards, or especially the Raspberry Pi, right, it's going to require a much more intensive round of performance analysis and tuning. So the other thing is that a lot of times where the time is spent is not where you may have thought it would have been spent. So here are some example ways of how you can execute less code. So the first thing is that every line of code you execute counts. When you're talking about an ARM v6 at maybe 320 megahertz or something like that. I mean, the Panda boards that we got by default started off at 320 megahertz. They were dual core. We had to crank them up to 920 to get it to perform at 60 frames per second. At 320 megahertz, you're talking really slow. Every line of code you execute really counts. And all those extra method calls, they all add up. So some systems, like normally on desktop, we always tell you, don't worry about it. The JIT will take care of you, right? It will analyze, it will inline, it'll unroll loops, it'll do all those sort of things. But like Bob Van Dette was saying at the keynote on Sunday, sometimes we can't actually do that because the cache size that's available on this little embedded system just isn't big enough to hold a method that is completely unrolled and inlined. And so we're actually going to have to execute more code in order to do the job. So on some systems, doing a lot of inlining is expensive. The VM isn't going to do it, and that means there's going to be more method call overhead. And all those excessive method method invocations, those are expensive. We have to create a new stack frame. We have to populate the stack frame. We have to do a jump to some other place, do some stuff, pop these things back off the stack frame, get back. And if you're doing that on tight inner loops, it can hurt you on some of these small systems. So, as a good practice, we ought to just reduce the unnecessary method calls. So here's an example of a method that happens a lot. This method is called compute pref width. Every region subclass anyway in the system has one of these. So every UI control and so forth has this method, and its job is to figure out what the preferred width of the node is given some height. And sort of the, I guess, simple way that you might have implemented it was to just say, well, let me get the insets and then get me the left of that inset, and then I'll add 200 to it, and then I'll get the insets and get the right. Okay, so the only problem here is that I've got, 4 method calls. Instead, let's just read the thing into a final variable, and then let's just, do those 2 reads. I got 3 method calls instead of 4. Okay, is this what we would call micro-optimizing on desktop? Absolutely. It turns out that this stuff gets called a lot, and on really small mobile devices, this sort of stuff matters. So, and it really didn't take you any more effort to write it this way than to write it the first way. You might as well just do it the right way the first time and be saved the effort. Now, the real question that you need to ask yourself when you are approaching a problem in terms of performance is, what is it that's limiting you? Why is the thing slow? It could be because of the fill rate. In fact, it's almost guaranteed that fill rate is going to be the thing that you run into. Fill rate is every graphics card has a limit as to how many physical times it can draw a pixel per second. And if you exceed that, it's going to be slow. I don't care how fast your VM is, your language, your algorithms, or anything else. If you got a graphically intense application and it's abusing the fill rate of the card, it's going to be slow. And we found that this happens a lot on these embedded devices especially. The geometry rate. So every graphics card, it represents your nodes and everything else are represented on the graphics as quads or triangles. At the end of the day, all the graphics cards deal with triangles and quads. And each one of those has a vertex, and so you've got 3 vertices for a triangle and 4 for a quad, or more if you do it wrong. And there's a certain limit, a hard limit on each card as to how many vertices it can handle or triangles it can handle per second. And if you exceed that, you're bummed. The thing is with JavaFX, it's very unlikely that you're going to hit this limit unless you're doing something like the Navis demo where they had the shipping containers and they had these models that they were importing from the 3D world that had bazillions of vertices in it. Then you can run into some geometry issues. But for your typical FX app, this is not likely to be a problem. CSS overhead, how much time you're going to spend actually processing CSS for your scene. It's possible. It's possible that you're going to run into some performance problems there, and there are some things that you can do to make that faster. Layout computation time. Like I say, the layout's called a lot. It's definitely possible that this can end up being an issue for you. So it's something to be aware of. We do a lot of caching. We try to only lay out the things that need to be laid out. So, it may or may not be an issue for you. Maybe. System I/O. Okay, on an embedded system, there's a very good chance that any system I/O you're doing is going to be causing you problems. And it's one of those things that generally doesn't show up in any of your Java profilers. If you're trying to profile the thing, you're like, oh man, this thing says I'm spending 50% of my time in this one method. I went and fixed it and it didn't change anything. Well, you're probably either fill rate limited, highly likely, or you're just doing some system I/O that's really hurting you. And it might be just the overhead of doing system I/O on the graphics side, because we draw onto some OpenGL surface and then we have to copy that whole surface over onto where the video card lives. And there's some overhead to that. So it just depends. Now here we have a button. All right, and this is going to be an example of a fill rate issue that you can typically run into with your controls or with other things that you try to draw, because buttons are drawn with multiple layers. In fact, for an actual button, the little the buttony looking part there that's in the middle is made up of 5 individual rounded rectangles that are drawn together. And this is what it looks like. So here's our fill rate. First, we're going to draw the background of the thing. Okay, graphics card is working to draw all those pixels. And then we're going to draw the next layer. And here it goes. You can sort of see the yellow in there. It's a little bit washed out on the projector. Whew. And then it's going to do another layer. Here it goes, working. And as you can see, I've got this purple rectangle guy on the top. Why did I spend all that time drawing the other stuff that was behind it? Well, I've got my little chalky edge, so I sort of had to draw some of it behind there, but there's a lot of pixels that I'm touching over and over again. In fact, more than 90% of all the visible pixels that you see here are being drawn multiple times, 3 times in fact. Okay, so when you have a certain fill rate, I'm abusing the fill rate right now, right? I am cutting in third what the graphics card is able to actually draw, physically draw. No matter how fast the rest of my algorithms are, I'm cutting in a third what the thing is able to do. So obviously you're going to want to try to improve your fill rate. There are some obvious, easy things that we've done for years in graphics. The first thing is, of course, to only draw what has actually changed. I was researching XBMC, which is a media player software, right? And I don't remember what's written in. It's either C or Python or something like that. And anyway, so there's the XBMC media player, and they were trying to port it onto BeagleBoard a couple years ago. They were having problems getting the performance up. And it turns out that they had only written XBMC originally for the original Xbox, and their philosophy was to just 60 times a second redraw the whole thing. Just keep redrawing the whole thing. And obviously it doesn't work on low-end devices, and so they're like, oh, well, maybe we should start doing, dirty regions, which those who are familiar with swing programming, we've been doing forever. I mean, this is a common technique in graphics programming since, I don't know, since way back. And the dirty regions, like if you're doing Android programming or swing programming, you, the developer, are responsible for knowing and figuring out what your dirty regions are. If you have a swing component, for example, and only a little portion of the thing has changed and needs to be repainted, you're supposed to tell the swing layout manager or repaint manager, you're supposed to tell it, oh, only this small little rectangle has changed. And that way, when swing comes back to render later, it will only ask you to draw that little piece and it'll have a clip there and life is good, and you'll get good fill rate. Well, Android, similar problem. The nice thing for us is the scene graph already handles this automatically for you. We know every single node that you've got, and we can just make sure that we repaint the little portion that's actually physically changed. We do all this work for you. However, if you use the canvas node in the scene graph, it's back on your shoulders. Or if you use writable images, it's back on your shoulders. You're going to have to manage, which portion of it has changed and what you want to draw again. For the rest of the scene graph, works for free. One of the other issues that you can run into is when we use effects. There are some effects that we use, probably most of them, that cannot, well, basically what they have to do is they have to draw everything first into a background image, and then they have to do an algorithm on that background image when it's drawn again onto the main back buffer. Okay, whether you're drawing to the main back buffer or you're drawing to an off-screen texture, it's still fill rate limited. You're still causing the graphics card to process multiple pixels, and that obviously is going to reduce it. So whenever you use an effect, it's going to cost you a little bit more. Now, like I said at the beginning, caution, right? This doesn't mean you don't use effects. Effects are actually almost free on your desktop system because desktops are so fast. But if you run into issues, that's one thing to look at because effects do come with some cost. There's another trick that has to do with clips. Now, in normal 2D rendering, if we did a filled rectangle and it was all, it was axis aligned and it was, it was pixel bound. So, you were exactly drawing the thing from, say, 100, 100 to 200, 200, right? It's a very simple algorithm. You know exactly what you're going to do. You're going to visit each pixel and you're going to just turn it on with whatever color you were told to turn it on with. Great. Now what happens if that same rectangle is, let's say, a half a pixel off? What do you want it to do? Well, if you had no anti-aliasing, then it would not, you would not see the little fuzzy edge. It wouldn't be 100 by 100 anymore. It would be a couple pixels smaller and it would have been adjusted to fit. Obviously that's not what we want, so we do anti-aliasing. Same thing if you took that rectangle and rotated it 45 degrees, you now have to do a ton of work on the edges in order to make it look good, right? Same thing with clips. When we have a node and we clip it, if the clip is directly aligned with the pixels and it's axis aligned, then we can do that clip very, very, very fast. But if your clip is rotated 45 degrees, we need to anti-alias the edge of that clip. That's going to take some time. In fact, what we have to do is first render your node into a background image, and then we're going to rotate that image and stick it on the screen, and that will get us the bilinear filtering and so forth on the edges, and it'll look good. That's work. So one of the things that you'll look at is if you're doing complex clips that are shapes, or if you're doing clips that are not aligned to pixel boundaries, doing clips that are rotated, that's going to cost you a little bit more. Again, on a desktop system, you'll probably never notice. But if your application is doing a lot of them, you've got thousands and thousands of these things, it's probably going to show up. Because what it has to do is draw first to an image and then draw to the thing, and now you're fill rate limited again. So that's always the problem. And then the last thing that, of course, you want to do is reduce the overdraw. And that was the example that we showed previously where we were drawing and then drawing on it again and drawing on it again. We need to reduce the overdraw. So here are some techniques that you can use to reduce the amount of overdraw that you have in the application. The first thing is to use image skinning. Now all the built-in default UI controls in JavaFX are all vector-based. And we did it that way, of course, so that whether you were showing it on a high-res screen or low-res screen or so forth, it would always look good. It's all vectors. And even more importantly, the reason why we did vectors was so that you could very easily change what the base color of a control is, and we can rederive all the new colors for it and draw the new thing. If you do images, it's a little harder to do. But when you're doing your own applications, there's nothing to stop you from getting a graphics designer and saying, crank out a whole bunch of images for me, and I'll take those images and I'll apply them to all my controls, and that's it. And in fact, we did a lot of that for the kiosk. We used images for various buttons and the popovers and so forth. So image skinning is good because you get the very complex look of the UI, but with no overdraw because you're only drawing one pixel for each area that you need to hit. So that works out really well for you. Another thing that we put into JavaFX 8 is an automatic region texture cache. In other words, you draw your normal button with vectors. We'll draw it smaller into a background texture, and then we'll stretch it from there in order to reuse it in other locations. So there's some caveats to it. Like, for example, if you have a button that's changing its height a lot, then it's not going to use the cache. If you have a gradient that is not going from top to bottom, if the gradient's going diagonally, then we won't use the caching technique. So it's one of those things that we just sort of turn on optimistically, or I say we turn it on when we discover that we've got a good fast path that we can follow for all the normal controls. So it's something that just sort of makes the vector-based stuff as fast as images, but with all the benefits of vectors. But you have to, you know, there are some things that will cause it to happen or not happen. So you may find, for example, that your application's working great, and then you styled it with a gradient that went left to right instead of top to bottom, and all of a sudden your performance is worse. Well, that's because you would no longer be getting advantage of the automatic texture cache. So the other thing you can do, of course, is just consolidate your background fills. Just simplify the UI style. So instead of doing 5 fills, you just do 1, right? That is obviously going to reduce the overdraw. You can reduce the number of overlapping nodes. So if you have a lot of nodes that are overlapping each other, then they're going to be drawing over each other, and you're doing a lot of overdraw. If they aren't overlapping, well, then you don't have that problem. Because actually reducing the number of nodes is not important for overdraw. It has no effect on overdraw unless those nodes are overlapping each other, then it does. So if you had 10,000 buttons just right next to each other and very small, doesn't affect fill rate. It'll affect other parts of the platform, but it won't affect the fill rate. If you have 10,000 large buttons, then that's going to make a huge impact on fill rate because you're going to be drawing the same pixel 10,000 times, once for each button. So here's an example of Metro. So one of the things that Microsoft did with their Metro UI was they came up with a slick, modern UI style that is very easy to draw. And they did this on purpose because they wanted something that would, well, be nice, but also be able to run on really dirt cheap hardware. So you'll notice that everything, like they're rectangles, they're not rounded rectangles. They're pixel-aligned rectangles. Very fast to draw. We've got fast paths for all that sort of stuff. When we see that that's what's going on, we take the fast path. Very easy. They focused on typography, which is cool, but typography really are just images, right? You take the path of the font, you render it into a texture cache. We do, not you guys, right? We do all this stuff for you. You give us a font, some random font, like whatever that people is. You say, I want to render it at this size. We go, okay, let me take that once. I'll take that P one time. I'll render it into a texture cache or a glyph cache. And then I have to lay that thing out twice. I just render that image in 2 different places. It's blistering fast. So, you know, they focused on typography, square rectangles. Life is good. I mean, look at that calendar. It's like made of nothing. So this was the point, right? Here's a bigger example of the same thing. You know, they just some images, which as we've seen have no fill rate issues. Solid rectangles, no fill rate issues. And some basic text. Those are glyphs, images, no fill rate issues, really fast. So this is something you can also do in your designs. If you're designing something on a small embedded system, you know, you have to take into account what that thing is capable of doing. And here's an example of Android is very similar in terms of the simplistic UI. It's nice because it also is modern. So, you know, it's sort of, we went from like the Baroque style to the modern style here, and it also is a heck of a lot faster. And if you think that's an accident, I don't think it is. I think I think everybody knows really actually quite well what these chips are capable of, and this is what they have to do to make it fast. Now there's another technique that we do on your behalf called occlusion culling, but there is something that you can do to help the occlusion culling engine. So this is very applicable. So basically, here's what occlusion culling is. I've got one of my rectangles, and then I got a yellow one, a green one, and a blue one. Okay? Now, suppose that the green rectangle becomes purple. Now, at the time that it became purple, you can see the dashed line represents what we have to redraw. We have to redraw that because the purple has a rough edge and there's some of that red behind it, so therefore we have to draw that portion of the red, plus you can see some yellow there, so we have to draw a portion of red, portion of yellow, portion of purple, portion of blue. Okay, so basically we have to draw 4 of them. So we really have to draw all 4 of them. Of course, we only have to draw inside that clipped area, but we still have to draw all of them. So dirty regions identified the red area for us automatically, but now we have to draw 4 of them. So there's going to be a lot of overdraw there, at least 3 times for wherever the blue guy is. Now suppose that the green guy, the blue guy becomes green. So now our dirty region is smaller here. Now the nice thing here is that we can say, hey, hold on a second. The green is completely above a solid opaque purple area. So I don't have to draw the red, I don't have to draw the yellow. I can only do this part. So this is what occlusion culling is. By not drawing, that is culling out things that won't be visible, we reduce the overdraw and we increase our rendering performance because we don't have that fill rate issue anymore for that particular area. Now, we will analyze, when you set, say, some CSS properties on a region, we will analyze those properties to determine what the opaque area is of your control. And once we know what the opaque area is, if anything on top of it changes, we can just say, oh, I don't have to render anything behind that because it's opaque. That's where I can start from. Now, if you use image skinning on a control, there's actually no way for us to do this. Because other than actually analyzing all the pixels in the image, we don't know which pixels are transparent or not. We don't know if the images necessarily has transparency or not. We can look at some of the headers and stuff of the images, but we're sort of limited a bit as to how we can automatically solve this problem for you. So there is a CSS property which I don't have on the slides. I think we called it FX opaque area, and or opaque insets. That's what it is. It's the opaque insets. So you can specify on any of the nodes what the opaque insets actually are, and we will honor what you say rather than trying to figure it out ourselves. So that's a way that you can get in there and say, no, I know this thing is some crazy image with transparency on the edges, but this is what the center is completely opaque. So this is what the opaque insets are, and therefore, when the JavaFX engine goes to render, it can do occlusion culling for you and avoid rendering everything behind you. Okay, so that's sort of our fill rate. Now, CSS was another potentially limiting thing that we talked about. So what are the costs associated with CSS? Well, there's parsing of the style sheet. There's whenever the ID or the style class changes of the node, then that node and potentially all of its child nodes need to be updated. So whenever you change the ID or style class of a node, there's a lot of CSS work that we have to do because we sort of have to refigure out the world, what happened down below us. On the other hand, if you change the pseudo class of a node, like say its hover state changes from false to true, it's typically very, very fast. Unless you have some children whose state is dependent on a parent's selector. So here's an example of this. This is a horror show right here for a CSS engine. Now, what this selector says is that if I have a child with the style class of child, and that child is a child of a parent with a style class of parent, and that parent's hover property is true, then I need to style it in a certain way. And what this essentially means when we analyze the style sheet is that we have to say, okay, there's a possibility as a parent node, whenever hover changes, that some child of yours down below has to have its style recomputed based on this rule that I've defined. And so we've got to go and do it. Now, there's a lot of heuristics and things that you can do with CSS. Complicates the code, takes some time, a little buggy, but we're adding all those things so that we can be smart about it and say, oh, well, only if the parent has a child with the dot child does it need to recompute this and that and everything else. But generally speaking, that's all work as well. So whenever you have selectors like this, it's just going to be more expensive. It just takes more work on our side to do the job for you. This is another one. Yeah, this is a very common, easy way to write your CSS, but there's a problem with it, which is that we don't know. This is a this rule will apply to any child with a style class of child that has an ancestor somewhere in the chain that has a style class of parent, which means that whenever we encounter a node of type child, we need to check it and every single one of its parents until we either get to the top or we find one that has a style class of parent. Now, in a case like this, it's probably not a big deal if you only have a few children in the scene graph. It's not going to be a lot of computational overhead. But imagine if, for example, we said a dot button who had a parent of some dot parent, and I had a table view with 10,000 buttons in it. Now I've got 10,000 buttons that all need to walk up the scene graph looking for a parent. In the case that they find it, it's not that bad. In the case that they never find it, you're going all the way to the root every time. You've got an O squared algorithm going on here. And, algorithms, takes time. This is another one. The set style, so you can specify a style just like you can in HTML. You can specify a style directly on Node, which is really convenient. I use it all the time. But you just need to be aware that it costs more, because when you do this, we've got to parse it, so there's some overhead there, and then we have to treat it in a different way than all the other styles that you find in the style sheet, so it gets inserted into some special parts in the code. And basically, we treat it as a separate style sheet that's been defined on this layer, and it takes time. So you need to be careful with those sort of things. If you're running into performance problems, that's something to look at. Now this is the honor parade or the honor show. This is the way that you would want to do it if you can. So this is a child whose immediate ancestor has a style class of parent. Okay, this is easy for us to do. Even if we had to do it 10,000 times, we're only checking the parent. This is very fast. We could do that. That's not a problem. Putting the pseudo classes directly on the node itself, dead easy, super fast. I mean, you can't beat it. So there's some things to look out for in CSS and other things that just really don't cost anything. So the question, does CSS cost you something? Well, yeah, it's work that has to be done. We're doing it for your convenience and all the power and flexibility. If you get into a situation where you really can't afford it, well, just do it in code. So here's a tip. If you're looking for performance improvement, avoid structural changes to your scene graph. On the kiosks, we had, it's about 1,100 or 1,200 nodes on there. And they're all there. We just set some of them visible false, as opposed to creating and pulling them off and putting them on and so on and so forth. There's cost associated with it. Why? Well, one is that whenever you change the structure of the scene graph, we have to reanalyze all the CSS from that point down, from where the change occurred on down. Because since you can have selectors that are dependent on the hierarchy, whenever the hierarchy changes, we have to recompute all the dependent selectors to find out what matches now and what didn't before. The other thing is, whenever you change the structure of the scene graph, we do structural integrity checks. So we go, is there a cycle somewhere? You tried to add this node to another node and you haven't been removed from the one that you're in, or you're trying to add your grandchild to be your parent or something like that. We need to do those sort of checks, and well, that takes time. So instead, what you ought to do, if you're going to do structural changes for the sake of changing the rendering order of something within the same parent, the best way to do it is not to remove it and add it back in, but just use 2 front and 2 back, because it's been optimized. There's actually another way to do it as well, which we'll mention here, which is that instead of doing 2 front and 2 back, you can also use the FXCollections. So the secret, what we're trying to accomplish with, as you know, in JavaFX, almost everything that has a list is of type observable list, which is an FX collection. And it lives in, I don't even remember the package, to be completely honest with you, JavaFX collection or something. And so they're all observable lists. You can add listeners to them, so forth. The observable lists are designed to handle mutation and event notification very efficiently. And so you want to make sure that the changes you make to an observable list are done in such a way that we can make efficient change notifications. And this is especially the case when you're doing, say, 15,000 monsters in GUIMark Bitmap. You know, you got 15,000 of these little guys and you need to change what order they're in so that they're not running on top of each other or whatever. You need to minimize the number of changes. Obviously, if you did 15,000 adds and removes, you're going to get 15,000 structural integrity checks. You're going to get all these notifications and everything going on. Waste of time. So you want to do minimal notification. And how do you do that? Well, for example, you can use the set all method that is defined on an observable list instead of clear and add all. So instead of first doing a clear it, now I'm going to add 10,000 items, you just say set all. And it goes in one notification and says, okay, everything's been replaced from here to here. And we can handle that very, very efficiently. You want to, like I say, avoid multiple add calls. So sometimes what we'll do on our startup code, for example, is we'll create just a normal list. We'll just go in some loop and add items to that list. And then once we exit the loop, we'll just take all those items and just do a set all on the observable list so that in one step we do the notifications. Life is good. Another thing that you've got is you have methods such as FXCollections.sort. Why would you want to use FXCollections.sort instead of collections.sort? Well, because FXCollections knows about observable lists. It knows about the notification. And when it does a sort, it can send a single permutation change event. And when it sends a single permutation change event, we can then say, we know two things. Number one, not only has everything changed from index N to index M, but we also know that none of the items were removed and no new items were added. They were just moved around from place to place. And that means we can avoid all the structural integrity checks and other sort of things. We just know, things have moved their order. I'm happy. I don't care. That's fine. I'll just go update the little peer. We'll draw it in a new order. Life is good. So permutation, very, very handy for us. So, we've built in a lot of these things into the FX collections helper static util class thing, and you ought to use it. Just this is a really good thing in order to avoid having to do a bunch of extra work. We know what a permutation is. We've got fast paths for it. And if you're writing your own listeners for a collection, you should also look at whether you want to take advantage of writing your own fast paths for these things. If you know that you can do less work on a permutation versus an add or a remove, then you should add some special handling for permutation events. Okay, the next tip is virtualization. So we talked about this a little bit in the keynote. List view is blistering fast. You can put 10 billion items in that list view and it'll scroll until its heart falls out. I don't know, whatever integer.max value is. Somebody knows. And the reason it's fast is because it reuses a small number of nodes over and over and over again. But reusing nodes is good, reduces memory usage. But it also is really smart in that it reduces the amount of CSS change overhead that goes on because it's not adding and removing nodes all the time, so it's avoiding all these structural changes. It avoids a bunch of layout changes unless it needs to do them. It avoids a whole bunch of invalidations unless it needs to do them. And basically it does everything else minimally. This is the whole point of our list view and table view and tree view, was to handle all this stuff for you. So really what you ought to do, if you can, is reuse the list view for anything that you need to virtualize in terms of, I have 10 billion items and I need to, cycle through them. That's what you ought to use. So in the schedule builder application, we use list view on almost every page. It's fast. It's really, really fast. So that's a good tip. There's another tip for you, which is manual layout. Now, we've got a whole pile of built-in layout containers, and that's good. Built-in layout's good. Tools know about it. Life is good. But there's a problem, which is that they are incredibly flexible, right? I mean, we're providing a grid view. We need to make sure that we can answer the question, what's the minimum size, what's the preferred size, all this sort of stuff, and what happens when the cell is bigger than the content? Should we position the content here, there, down here? But we've got this big pile of code. We got to compute all this stuff. If you're doing something simple, what you ought to do is just do your own layout. So a lot of times what we'll do, Jasper and I will do this all the time, we'll just create a new class and extend from region. The reason we extend from region is so we can style it from CSS, but otherwise it's just a basic parent. You can add children to it and then you can lay it out. When you extend region, you almost always have to implement the compute pref width and compute pref height. Not always, it depends on your usage of it. So here's another thing too, right? If you're creating a subclass of region for your own use, you can cut corners left, right, and center. And doing less work will get you better performance. If you're creating something that's supposed to be reusable by the rest of your company or something else, you're going to have to do more work and be a little bit more serious about it. So you could probably avoid overriding compute pref width and pref height if you know that you are manually going to resize this thing to a certain size, or you're going to specify, you're going to hard code what the preferred width and height are, and you don't have to do it. But almost always you're going to want to implement compute pref width and compute pref height. And of course then you have to also implement layout children so that you can put things exactly where you want to put them. So custom layout lets you cut corners and just sort of put things where you need them. So here is what happens during layout, the sort of things that JavaFX is going to ask your layout container. It's going to ask you, how wide would you like to be? Or how tall would you like to be? What's your preferred width and height? And what's your maximum width and height? What's the biggest that you will allow? And I also need to know, what's your smallest size? Because, I mean, I don't want to allow you to get resized to be smaller than what you want to be, right? I mean, and by the way, is your width dependent on your height? Or is your height dependent on your width, or neither? And do you have a baseline? Where is that exactly? What should I consider your natural position, your natural width and height? Like if you're a text node, you're not at 0, 0, you're at, 10, 10 or something, I don't know, but what's sort of your natural layout bounds position? I'll take that into account so I can put you where you need to be. Okay. Oh, by the way, can you be resized or not? Okay. These questions are asked for every node during layout. We're asked all these things at least once, sometimes 20 times. I mean, it's out of control. And we ask a lot of questions. So, I don't know, just why I'm saying that sometimes you want to do custom layout because you can avoid a lot of those questions. You just sort of put things where you want them and that's that. Another thing that you can do is if you manually specify, you can manually specify in code what your min width is, what your pref width is, pref height, max width, max height, and so forth. Those overrides, if you specify them, we won't ask those questions of the layout container. It doesn't have to compute anything. It'll just grab them. So that's another way to sort of short circuit the amount of work that goes on during layout is if you manually say, look, min size is 0, max size is integer.max value, and pref size is, 200 by 50. I don't care. You just give it something, we won't ask any questions. We'll just go about sizing things to what you tell us. But there's a lot of times when you don't know. Like, for example, if you have text. What are you going to do, right? Its height depends on its width in all languages that run left to right or right to left. So here's a tip. When you're dealing with that situation, it uses a thing we call the content bias. So the content bias of a node is either horizontal or vertical. And what that means is which way? Horizontally, are you more important and your height depends on it? So does your height depend on your width? If so, you're horizontally biased. If your width depends on your height, then you're vertically biased. You want to be a certain size vertically, but you don't care how wide you are horizontally. So you're biased towards your vertical dimension. Okay? And if it's null, then width and height are completely independent. So content bias is what you would use for handling some of these situations. Now content bias null is by far the fastest because when we compute a preferred width and a preferred height, if we know that your width is independent from your height, then we'll just cache that value that you give us and just save it. So that the next time the layout code is asking it or the next time somebody else is asking it, we already know the answer and we can return it without having to compute a new pref width or compute a new pref height. So, if you're truly independent in both axes, then that's what you want to do. So, labeled controls, for example, if you don't set the wrap for it to be word wrapped, then we're independent in the width and the height, and we can just be fast. If you're doing word wrapping, well, now our height depends on our width. We have to take some different code paths. So content bias horizontal is common for text with a wrapping width, like I was talking about, right? By far the most, it's usually content bias is either null or it's going to be horizontal. That's the typical thing. Now, the unfortunate thing, and I discovered this leading up to Java 1, is that content bias, when it's not null, is actually not very well handled by our current layout managers. There's bugs on it. People have had some problems that they've talked about in the forums. So, unfortunately, it's a bug, and we're going to fix that for JavaFX 8 so that we handle the content bias correctly. But just so you know, in your own code, if you're doing your own layout, there are methods. It's all well documented how it's supposed to work. It's just that our current implementations of our layout managers are not handling it correctly. So something to be aware of. Okay, so all that was rule number 1, which was do less work. I did a lot of work for that. Rule number 2, right? Know your device. So these things are really interesting. So here, this is the NVIDIA GeForce GTX 690. It was the top of the line on their website. I went to their website yesterday and I said, okay, what? Yes, I was working on my slides yesterday. So I went to there and I said, okay, what is the absolute fastest graphics card that they have? This is the guy, right? He's got over 3,000 cores in this graphics card. 234 billion texels a second or whatever this thing can push, right? Look at it, it's got 384 gigabits per second on its memory bandwidth. And my favorite is that the graphics card itself requires 300 watts of power in order to operate. All right. I mean, wow. This is one of their lower end. It's just a very modest 16 cores on this guy. It's like, I don't know, 8 gigabits per second, right? That's not bad. 30.5 watts. I mean, this guy's like a regular hippie. He's like, he's just doing his part. But even this thing is a fire breather compared to what you've got in your latest Apple iPhone 5. That little graphics card, yeah, he's got 3 cores. And that's one more than the last version of their graphics chip had, right? There's only so much you can do with 3 cores. And you know that thing's not sucking 300 watts of power. That thing is just sipping away at, I don't know, 1.5 watts or something. These mobile and embedded devices, they're just different beasts. You have to go into it understanding that JavaFX is giving you a single development platform and API that spans on all these devices. But you really have to know what you're trying to target to know what you can do and what you can't do. On some of these guys, like if you're trying to write a media player on a Raspberry Pi, you're going to have to write your application differently than you would if you were doing it on desktop. You just have to know going into it that you've got a very bad CPU on the thing. It's just slow. So it's got a good graphics card though. So but the bus speed on the thing is abysmal. And so at the end of the day, you got to try to figure out how you're going to make your application fast on that device. So that's just the way it is in the world. So here's a basic rule of thumb. On desktop, you should be able to handle 20 to 100,000 nodes. 100,000 is definitely on the high end. Maybe not all of them are visible, but you could have a scene graph that big for sure. And you could probably, depending on how the fill rate and everything is, like I say, if you tried to do 100,000 nodes and they were all overlapping, you're dead. If you have 100,000 nodes, but a bunch of them are outside the window, they've been clipped off from the screen, it's probably going to be just fine because you're not going to be fill rate limited. And if you're on a desktop and we've got, 3.5, I don't know what, quad core, 3.5 gigahertz chips or whatever, I'm sure we'd have no problem processing all that stuff. So on desktop, you can build some. If you do less than 20,000 nodes on desktop, I mean, we're going to be offended. We're like, what? Why are you using us? All right, 500 to 1,000 nodes on embedded. This seems to be about right. So, like I say, our schedule builder app was, 1,200 nodes or so that was in that thing, and it was fine. It's a happy camper. So, you're going to have some fewer nodes that you can handle on those smaller devices. A lot of it's just memory, right? It uses more memory to have more nodes, so you have some fewer, and you have to sort of take the hit on the structural changes from time to time, perhaps. But you can actually do a lot with 1,000 nodes. Now, when you get into small embedded, like let's say that you were trying to do you know, a little touch screen for a printer, and the thing was 640 by 480 or 320 by 200, you know, and it's running on some little measly, you know, 20-cent chip or something on the back end of that thing, you're going to have fewer nodes. So 100 to 200 nodes is actually pretty typical for, say, a Java ME class sort of small device. But they usually have much smaller screens, and they're usually like, you know, not, actually if they had a high pixel density it'd be even better, but you have to draw big buttons, right? So on that 320 by 200 screen, you've got, you know, 100 by 50 of that is just one button. So you don't really have that many nodes on such devices anyway. But, you know, you just have to be aware that you've got a much smaller space that you can fit things into. It just depends on your hardware. If you had a small screen and the thing was backed by, you know, your latest Intel chips, then, yeah, go ahead, put 100,000 nodes on there. It's not like it'll matter, but, you know, knock yourself out. It just really depends on what the hardware is capable of doing. Now, here's another tip, and this one we've talked about before, which is caching. So I have some scene graph. And this scene graph, I'm going to draw it. And there's a lot of work to do to draw this scene graph. And then it produces this nice chart. Okay, so I have my graph. I did tons of work. I produced myself a chart. And, you know, the thing is, if this chart is never going to change, then by George, you ought to cache the thing. Assuming that you're animating it or moving it around or changing its opacity or something like that. If the chart's nodes themselves aren't changing, man, cache that thing. Because if you do, this is what you'll get. You'll draw once to an image, and then you'll draw it a bazillion times to the screen. And it'll be a lot faster because you won't have to do all the processing. And, you know, if there's clips and all these other things and these rounded rectangles and intermediate textures and all that, yeah, you avoid all that. You just got one copy of it, you just draw it a bazillion times. Now, on some devices, you actually can't do that. It's very interesting, actually. On some of these embedded devices, you don't have enough texture memory. I think the boards that we're using out there, the Panda boards, had, was it 42 meg or 36 meg of texture memory? VRAM. 40. So it's 40 meg of VRAM on that thing, total, okay? On those other devices that we showed you, I mean, you got, you know, 256 meg, 512 meg, whatever. You got all kinds of it. So you can cause yourself problems by using up too much texture memory. On the other hand, sometimes this is exactly what you want to do. So for example, when we do animations, a lot of times we'll turn cache true, and then we'll animate that thing off the screen, and then turn cache true to cache false again. That's the sort of thing that you're going to want to do. And like I said on there, it backfires if you're changing the thing a lot. So if your chart is animating, you're hosed. Another thing is the cache hint. You know, there's different cache hints. You can choose how you want it to behave. You've got speed and quality and whether it's rotated and scaled and so forth. So you can tell, because here's the thing, right? If you render to an image and then we rotate the image, we have to do some form of interpolation to figure out what the pixels are on the edges and as it's rotated. And we can, you know, we can do that very quickly. Or we could rotate it and then ask you to redraw all your stuff, and then you know, it'll be much more precise. So it depends on what you need. If you're just spinning this thing off the world, then just set it to speed and you're good to go. If you actually care when it rotates that you redraw things, you're going to need to set it to a different setting. It just depends on your specific use case, but the cache hints are there for you. All right, I think this is the last little guy. Now this is just added in JavaFX 8, so it doesn't work in the shipping 2.2, and I think this one is probably going to be there forever, but don't quote me on it yet, because we're still in our development builds of JavaFX 8. But it's a really handy little guy. So if you set this flag, JavaFX.pulseLogger, to true, we print out a ton of crap to your console. And this is a single pulse. Now in JavaFX, we have a pulse that occurs, if you're doing a lot of animations, it'll happen 60 times a second. Or if you have a lot of animations but everything's slow, then, well, you'll get a pulse as frequently as you can. And if you're not really doing a whole lot, you'll get pulses intermittently, only when needed. And during the pulse, we do CSS, we do layout, we kick off a drawing and everything else. Now, the pulse logger is going to log all sorts of different things that occur during a pulse. So, for example, at the top here, you can see a pulse count. This one's pulse 1. If I had had 10,000 pulses in my application, it would say 10,000. So it's just a different number, incremented, auto-incremented number for the pulse. You can see the duration, which is how long did this pulse take. This particular pulse took 250 milliseconds, which would typically be a bad thing because 16 milliseconds is all you can get and still get 60 frames per second. So this thing is soaking up a ton of different frames. So we're running at like 4 frames per second is what this thing's running at based on this pulse. You can also see the time since the last pulse over there, 989 milliseconds, which means that there was a long period of time from the last pulse to this one, and this one took a long time to complete. Then you can see over here that it's got multiple threads. It's got T12, that's thread 12, and T10, which is thread 10. Well, of course, we have two threads. We have a render thread and an FX thread. So we can see that the FX thread, thread 12 in this case, did a CSS pass, which took 8 milliseconds. That's half of our budget right there for our 16 millisecond budget. He used half of it. The layout was only 2 milliseconds. So in this case, layout wasn't my problem. 151 milliseconds waiting for the previous rendering. Okay, that obviously is the lion's share of why this pulse took a long time. It's because he couldn't start a new render job because the last one was still going. So whatever happened at the beginning is taking a long time. Let's see here. He copied some state to the render graph because we have two threads. We also have two copies of the state, and we copy it from the FX side to the render side so the render side can go do what it needs to do. That only took 2 milliseconds. That wasn't too bad. Wow, 24 milliseconds to compute the dirty ops. So the dirty ops is the thing that discovers what's changed so that I only have to draw the little portion that's changed. A lot of time there, so that would be something that would be worth looking into or filing a bug if you could make it reproducible. Boy, and then we can see that we had two actually independent dirty regions to render. So if you have a large scene and something changed in one corner and something changed in the other corner, instead of redrawing the entire scene, we'll actually do two separate paint passes, one for the top left, one for the bottom right. You can see in this case, that's what it did. Two different dirty regions to render, and then we can see one of those took 54 milliseconds and one of them took 4 milliseconds. That's pretty useful information, help you get to the bottom of what's going on in your particular pulse. And then at the bottom, there's various counters that we put in, and these are really easy for us to change what we've got. But so for example, I wanted to know how many nodes were actually rendered as a consequence of this pulse, 70 of them. And it's amazing that 70 of them took 54 milliseconds. Wonder why. Maybe I'm using effects wrong. Maybe I'm doing something going on there, but that's something to know. How many nodes did I have to actually physically visit in order to render this thing? 143. How many times was I telling it that it needed to layout? Well, there were 122 dirty nodes that needed layout. Interesting stuff. So the pulse logger is there for you to, in JavaFX 8, that you can print this stuff out, kind of get a feel for what's going on in each of the pulses. And it's a good thing to feed us as well if you run into a bug, because you can say exactly sort of what was going on in your application. So I end the session the same way that I started, with a caution that you ought to write the clean code and then profile, because if you overdo it, you're going to end up with an unmaintainable mess. Generally speaking, everything will be just really fast. But you may run into cases where you get periodic hiccups. Things were smooth and then it was slow. Why is that? Turn on the pulse logger, see what happened. You may run into cases where your application is just grinding under 80,000 nodes and you say, well, it should be able to handle 80,000. I've got a big expensive machine here. Why is that? You can go in and take a look at some of these tips and tricks. And thank you, and we have 1 minute for questions.
On laptop with integrated HD 3000, I noticed that even if I have accelerated FX, accelerated enabled, text transition is done like in Java 2D, and it's not smooth when text stops. It's a kind of switch to accelerated paging. So when I disable accelerating, everything is smooth, but performance is not as good. Is that something wrong with the driver, graphics card, or is that something that you'll be able to fix?
It's hard to say, but what you could do, I don't know if you filed an issue on it, but the thing to do in that case, if it's simple and reproducible, the way that I would file that issue is by doing two things. Well, if you could turn on pulseLogger in JavaFX 8, that'd be 3 things. One would be to have that, gives us some information. But really, if you can just take a screen capture and attach it to the issue, and the little chunk of code that would reproduce the issue and put it on there, and of course tell us what your graphics card is, then we can look at it. Sometimes what will happen is people will they'll log an issue and it'll have the code, but we can't reproduce it. And we're like, I don't know what to do with this one. So it just goes into the backlog. But if you have a video or something that we can look at, then we can go, wow, that is really bad. And then we can, work with you on getting that taken care of. But off the top of my head, I couldn't tell why that would be the case. All right. Oh, it's lunchtime. Thanks, everybody.